Hi students, welcome to my lectures. Okay, this is what we are in the PVT estimations. If you please follow my lectures from the beginning. Okay, we are in the estimations of volumes with the pressure and temperature informations for liquids as well as the vapors, because there is separate set of procedures and equations that are available to estimate the volume informations. Okay, to do that we have to go through we have constructed, because there are certain things that are necessary for you to estimate the volumes, and the first thing that we have gone through is constructing this PV diagram. In the PV diagram we have observed that this particular blue line, and if you maintain the pressure and volume, volume conditions, it is fallen in this region, it is called a subcooled liquid. If it is on the right hand side of this particular red curve, it is on the vapor side. If you maintain the conditions which falls in between the region, it is called liquid and vapor regions. Okay, we have constructed this particular graph using this particular experiment. That means I am identifying the change of phases from by increasing the temperature from liquid to the vapor state. So I have we have gone through that what happens if we slowly add the heat. The transitions from the liquid to the vapor state happens. In between, the saturation conditions will come. So this is how we have constructed, by keeping the pressure as a constant. So now we are going to construct the same graph using different approach. That is called by maintaining the temperature constant. Assume I have the set of piston and cylinder assembly which is dipped inside the temperature controlled bath. Here the temperature of the bath is maintained. You can see the constant heater system where all the piston and cylinders are dipped inside this particular bath. That means the during this transitions from the liquid state to the vapor state, temperature will not change. So what that is going to change, that is making a substance which is at a liquid state to the vapor state. So because now I am changing the pressure. Earlier I have changed, in the previous lecture we have changed the temperatures. Now we keep the temperature constant, and let us observe what happens if I change the pressure. Assume at the stage, because the substance, I have a different states A, B, C, D, E, F, G, H, I, J, K. So at different states, let us start with the liquid state. That means I have kept a certain amount of blocks on this particular liquid which is exerting certain amount of pressure at the same temperature, that all piston and cylinder are at the same temperature. So what happens? Now it is a liquid. Let us start with the liquid state. At this particular state A, the pressure is PA and volume is VA. We have to plot this pressure and volume information on this particular graph to map what is happening in this particular change of states. What happens if I remove one, because I have kept 11 blocks here. Assuming the pressure is the pressure which is inside this is of a pressure that is exerted by these 11 blocks. What happens if I remove the one block? Now it is a 10 blocks. That means the pressure has reduced. That means because the pressure is reduced, the volume is going to increase. Okay, that means earlier it is the pressure PA, highest pressure. Now suddenly you have removed one block. That means now volume has raised. That means during the drop of pressure, volume is increasing. That is this particular from state A to state B. Okay, of course this is natural. What happens if you remove one more block? That means the conditions at this particular state are PB and VB. If you remove one more block, it will still the liquid is going to get expanded. So the pressure here is of 9 blocks, which is PC, and volume here is VC. And now, even though you try to remove a block, suddenly it will go from different change of states. That means liquid will entirely become a vapor if you try to remove this 9th block. That means you are at a saturated conditions. You know, in the earlier class, what we have noticed, and during this, there is a change of state that is going to happen at saturated conditions. That means if you try to remove small 9th block, suddenly the liquid will start becoming a vapor and will become a complete vapor. Okay, from PC to pH, even though you maintain the same pressure, sudden transitions happens. It will become from liquid state to complete vapor state. That means from PCVC to pi vi. You can see the pressure is remained constant, but the volume has increased drastically because the liquid volumes are low compared to the gas volumes. As the liquid is becoming the vapor, the volume increase takes place at the constant pressure. Okay, that is why Pc equal to Pd equal to Pe equal to Pf, Pg, Ph, Pi is nothing but P saturated. That means you are in the saturation pressures and temperature condition. That means at this particular temperatures, if you maintain this particular 9 blocks pressure, that means you are in the saturation zone. Wherever this transition happens, from the liquid to the vapor, that means at this particular point to at this particular point, now it is at the saturated conditions. It's saturated in the conditions in the sense, if you keep, that means if you try to evaporate the water, the entire water can become a vapor at 100 degrees centigrade if you try to add up more amount of heat. This is called the saturated conditions, okay, where we can observe the complete change of phase transitions can happen. So what happens beyond? Oh, of course, slowly at 9 blocks pressure only, from liquid to vapor, completely it has got converted. What happens if you try to remove the block? Okay, imagine, okay, 9th block, okay, complete transitions, 9 image. Okay, after this complete vaporization process, if you remove the one more block, what happens here? The volume expansion takes. Now the vapor volume only, it starts getting expanded. Here only liquid volume will expand. Here vapor plus liquid expands. Here only vapor volume will get expanded because there is only one vapor phase is present, the other phase is absent. So this is beyond this point, it is called superheated vapors. That is why they're indicated by red line. Earlier it is called saturated liquid, subcooled liquid. It become a liquid plus vapor, which is called saturated conditions, and beyond certain point it is only vapor. It's called a superheated vapor. Okay, that means entire this experiment is conducted at one particular temperature, because I am maintaining the temperature in the bath, which is temperature T. What happens if I conduct the same amount of temperature at same experiment at different temperature? Let us see what is going to happen. Now we can because I am only interested in this particular region, liquid plus vapor and vapor. Let us mark only this liquid plus vapor, or let us mark all these three at different temperatures. What is going to happen? See, the graph has emerged out. That means if I am conducting the same experiment at different temperature, you can see the T1 experiment, T2 temperature, T3, T4, T5, T6, T7. If I continuously increase the temperatures, that means bath temperature, and I conduct the same experiment, I am going to, this line got shifted to the upper side. If I conduct the experiments at higher temperature, if I conduct the experiment at lower temperature, this line will get shifted to the bottom. And out of this, if I join this blue curve, that's a saturated liquid. That means if I point out locus of all the liquid at the saturated conditions is the blue one. The locus of all the saturated vapor, if I mark it as a red curve, it's called the saturated vapor curve. That means on left hand side I can find the complete liquid region. On the right hand side I can find a complete vapor region. If you go beyond a certain point, it's called above this critical temperatures. Okay, this is called completely fluid or vapor regions. Only you can able to identify in liquid and vapor below this TC. If you go beyond TC, you are not going to find any liquid. It is completely vapor. Only liquid and liquid plus vapor and vapor can exist only beyond the critical, this particular temperatures. If you even go beyond, it is completely vapor. Okay, there is no liquid phase that is existing, because you can see it's entirely red curve. Okay, so what advantage we are going to get from this PV graph? That means if you somehow know you are on the left hand side of this equation, what is this line denoting? PV line, right? You can see this blue line. Take any one line at this temperature T1. If you're trying to make a line, this line is denoting pressure and volume information at this particular temperature T1. Okay, what is this particular line? It is at a different temperature. At T2 temperature, what if you maintain this particular pressure, then what will be the volume? if you maintain T4 temperature in this example, this kind of pressure container, I mean kind of piston cylinder assembly or this system, if you are maintaining T3, if you are maintaining the P7 pressure, and what will be the volume of this particular liquid. So you can able to, this line is giving some information about pressure, volume and temperature information. Similarly, if you go beyond, I mean vapor region, what this line is indicating at the T6, that means you are trying to, if you maintain the temperature T6 in this container and pressure P4 example, or P5, if you maintain the pressure P5, if you maintain the temperature T6, then what is the volume of the liquid? You can able to get the information from the graph. That means these particular lines are called equation of state lines. That means, what is the equation of state? Any equation connecting the pressure, volume, temperatures information is called equation of state line. On left hand side, it is called liquid equation of state lines. On the right hand side, it is a vapor equation of state, equation of state lines. There are number of equations of state which can able to give both liquid volumes as well as the vapor volumes, or completely vapor volumes. Okay, this is called construction of pressure, volume, temperatures. Okay, I mean this is all very important because this is the basic background to learn PVT, pressure, volume, temperature data. Okay, wherever it touches, you can see at T1 temperature, if you maintain the P1 pressure, okay, example, then these, wherever it touching this particular blue curve or red curve, those are called saturation pressures and saturation temperatures. So P3 and T3 is called the saturation pressure and saturation temperature. P4 and T4, it is touching this line, is called saturation pressure and saturation temperature conditions. So majority of the information we can able to get from constructing the pressure volume diagrams. Okay, I hope now you get a idea, because this is the idea that is required to go for the PVT calculations. And before we go to the pressure, volume, temperature calculations, now it is time for us to identify that whether we are in the liquid side or a vapor side. How we can able to identify? The next phase is that beyond after the next phase, we will about to calculate what is the volume for a given pressure and temperature for the liquids, and what is the volume for a given pressure and temperature conditions for the vapor, or what is the volume of the vapor for a given pressure and temperature. Okay, all the informations we can able to get, which is required for as such to connect the pressure, volume and temperature. Thank you. Let us move ahead.